So please confirm that you would like to register. Could be useful for you members of the International Advisory Board to eventually recheck some points. So thank you again very much for being here. The presentation of today is pretty strong with a lot of contents. So we will try to check all the slides that we prepared. Only one starting information. The core of today will be the review of the technical part of the project. So in the material that we prepare for you, there are also some other stuff. For example, there is one section related to didactics, the other one section related to the reports of each researcher. And then there is also a comparison that you asked to us last year between our ICE, International Industrial Computer Engineering Lab, and some other more or less equivalent or not equivalent laboratories. So with respect to questions about these other topics, eventually we will exchange emails in the next days. So let we devote this presentation to the technical part, otherwise we do not have time. So my presentation will cover the first 50 minutes, more or less, and I will show at first the project goal update. We arrived to the final goal of the project, and I will particularly describe the final demonstrator. And then on top of this final demonstrator, all my colleagues here, which has been grouped in a coherent research group, will make the presentation of the research outcome. The presentation at the end has also some information about exploitation and dissemination. If there will be time, we will discuss about them. Otherwise, we will leave them to eventually mail. So our goal is in the direction of what is starting to be called Industry 5.0. This term is not completely accepted yet by the international community, but the trend, I think, is pretty clear. That is, the trend is moving from what is currently called Industry 4.0 to Industry 5.0. And I will explain better in the next slides. Why we take a look to Industry 5.0? Because last year, correctly, you asked us to identify a real and innovative problem and try to converge all project activity to solve the problem. That is the problem that we proposed last year about the transformation of graphical stuff into a receipt and so on, sounds to must artificial. So we tried to face a real problem. And the idea has been to try to identify our role in the current shift from Industry 4.0 to Industry 5.0, and to identify a demonstrator which is able to include all competence of all of us to describe what is necessary for designing an application, an infrastructure which is compliant to Industry 5.0. So the final goal of the project could be the definition of theory, methodology, and tools to build a completely reconfigurable production line able to interact with humans. Able to interact with humans because, you know, perhaps better than me, that the trend from Industry 4.0 to Industry 5.0 starting from the fact that it is very superficial to consider that humans are no part of a production line. Humans cannot simply be the inspector of the production line, checking data coming from the production line and eventually controlling them. Humans workers are still an important issue, an important functionality of a production line. So they should be included then, and they must be part of a robotic or an automatic production line. In other terms, we can say that the typical characteristics of Industry 4.0, that is interoperability, virtualization, industrialization, service orientation, modularity, could be altogether collected to the slogan that humans have to understand the robotics behavior. On the contrary, if we move to Industry 5.0, we have to add reconfigurability, which could be also something related to the current Industry 4.0, which is on the border, but the configurability is very hard to be reached in a complete way. But then we have uncertainty because we have the unpredictability of the human behaviors. They are not deterministic. We are not deterministic. We have cognitivity because we have to give cognitivity to the machines to understand humans. And obviously we have safety because in this very well integrated behavior in which humans are working with robots, we need to increase, to extend the level of safety. In other terms, we can say that Industry 5.0 is the industry in which robots have to understand human behaviors. So going in this direction, our industrial computer engineering HICE lab has the goal to arrive to have a complete configurable production line able to interact with humans. So you know that our timeline, our roadmap is more or less arrived not to the end. We still have this year, the 2022, but at the end of this year, the project has to stop. So it is very harsh to imagine to arrive to a complete integration of humans and robots by the end of this year, but we would like to arrive to have a production line with all the preconditions, with all the main characteristics that allow to integrate humans and robots. And then, by the way, we still have new projects that are based on the same infrastructure. One project is called Opera, and it is exactly related to the safeness of workers, and it is based on the same infrastructure. And we are currently competing on some funding coming from the recovery fund arriving from the European Commission to Italy to recover from the pandemic. There is a very large set of fundings, and to be able to obtain money from this direction, we put exactly our laboratory on the table, and we obtain very interesting results with this. So we have been involved in many proposals, and for sure, at least one of those will be funded. So we will continue at the end of this year in this direction. So this is important because this project does not end to the last day of this year, but it will continue for sure in the next years. So starting under these assumptions, we arrive to define the final demonstrator. Sorry for this picture, it's a bit a mess, but I try to explain it as better as possible. So let me start from the phase 0. So in the phase 0, you have to imagine that a new person will enter in the laboratory. By the way, at the moment, we implemented some parts of this final demonstrator. All such parts are not connected yet together, so we are not able to make a complete show. But by the end of the project, when there will be the final review meeting, when I hope you will be here in Verona to make this meeting face-to-face, you will see for sure all this demonstrator working because we are perfectly in the roadmap. So imagine phase 0 that a new person enters in the laboratory, okay? And this new person with a tablet will check which kind of objects can be designed, can be produced by our production line. So the definition of the project, of the object, is not fixed. That is, there will be some characteristics which can be combined together. And by combining such characteristics together, we arrive to have an exact object to be produced. This produced, so a new recipe. This new recipe for the production change the configuration of the entire production line, modify and configure the manufacturing execution system, and the manufacturing execution system, based on this reconfiguration, start to extract pieces from the vertical storage. All such pieces are managed by our mobile robots. More or less, such pieces are parts in plastic, which has been printed by our 3D printers, and some boards, electronic boards. All such parts are put together, and they are programmed by passing through the functional control machine, which is also able to program the electronic board. During this check and this program of the electronic board, some information are put on top of the board. For example, in the case of we would like to recognize the person that enters in the laboratory. Such information could be the name, the surname, some other stuff, what role has this person in the laboratory, and so on. At the end of this programming, okay, all the parts will be assembled together by our assembling unit. This assembling unit has been extended, for example, with a tool for skewing all the different pieces, and all pieces together are then checked by the visual control stage, and finally they are released. To release them, there is another mobile robot that arrived to pick this piece, and this robotic mobile robot goes to the person that started this project and gives this piece to the person. The person takes this object and put the object on the body, okay, it could be something which could be wearable, and perform a kind of movement. For example, it shakes the object. By shaking the objects start to be activated because there are apparatus into the chip that allow to recognize these movements. And also all the infrastructure, the camera infrastructure that we have in the laboratory recognize exactly which is the person among all workers which perform this operation. So we have a connection between the person and the information which are transmitted by the object to the data collection architecture, and all such information are used by the digital twin of the entire infrastructure to certify that the specific person is no longer unknown, but now is Franco Fumi, which role of a standard worker. And now Franco Fumi, starting to move in the laboratory, can have some specific possibilities to manipulate something or not, depending on the role. So we close the loop in which something which has been created becomes a part of the digital twin of the entire laboratory. Obviously, all such stuff must be executed on top of the computing architecture that we implemented in the CR, and also by using all the software that we have. This demonstrator, we succeeded to check, has been useful for all the researchers that we implemented in this year and that we would like to finalize during this year. So the next slide, after this one, try to go in depth into the different parts of this demonstrator, but it is not important now. Eventually, if you have more interest, you can go there to take a look. But what is now important is to move to the slide 38, okay, and 39, when there is the list of all technologies that have been implemented on top of this demonstrator, which are currently implementing. And you can see in this table and the table in the next slide, which is the specific research that we implemented with the specific technology, which is the role in the demo, and which is the slide on the slides that describe this research. For example, let me make a first example with respect to cyber-physical production system modeling and reconfiguration. Okay, the first research has been on the automatic definition of a receipt and automatic configuration of the mess. This is related to phase 0 of the demonstrator that I've just described before, and in slide 42, there is the description of this research. Now there will be one colleague, at most 2 colleagues for each group of researchers that will describe to you the main results. There will be 3D printing, the computing architecture, pardon me, data management, mixed reality, image analysis, advanced robots management, safety in a human-machine environment, security and privacy, and finally, validation, verification, and testing. Okay, I don't know if you have a question about the demonstrator already, or if we can start with the different researches. Samajit, yes, no problem. You can interrupt me as you like.
Okay, thank you, Franco. Yeah, so that was extremely impressive. I just have a simple question. So of course, I find it very interesting, how you designed it, that the operator, which was Franco Fumi, who shakes the item, and then this is recognized, and then the person can participate. So could you maybe briefly explain what is the advantage of doing it like this versus just typing in a command or pressing a key? What is the particular advantage gained by this action of shaking and that triggering subsequent things?
Okay, you have perfectly right. That is, we can imagine to obtain the same result in a different way, eventually easier and eventually with less expensive. But we wanted at first to connect all together all the technologies. So this is a way to solve different problems. And the core of this demonstrator is how to produce something which becomes part of a digital representation of the production line configuration itself, and how to design something which requires a reconfiguration of the production line. So this was the main ideas, and we identified this way. But then, for example, having an object, a wearable object that is able to recognize you is typical of a lot of situations. So we use something which is pretty standard. The production ad hoc of the object for a person is not so standard, and this is the nice part of this.
Understood. Thank you.
Franco,
yes?
I would say that, yes, this is quite interesting. On the other hand, the interaction between a human and a production line has to be, characterized better in terms of the advantage that such a collaboration gives, right? So because in the big production lines, actually the fewer men, the better. And while in the small precision manufacturing lines, small and precision. I want to underline these two words. When the collaboration with humans is important, but one of the things that is look at especially in this domain is how robot can learn from men who actually do the operations. So the collaborative learning.
You have perfectly right. And in fact, let me say that what I've described is the baseline of our results. So we will sure that by the end of this year, we will arrive to this configuration, which is the baseline. On top of this, we are already implementing some evolution. For example, one evolution is that when the worker, which is allowed to do it, goes in front of the robotic cell and perform the skewing operation instead of the robots recognize that this has been done and do not perform this effort. This could be one for sure evolution. The other evolution that we show to the robots how to do something, and this become part of the recipe of the robots, is another evolution. We are not sure to be able to arrive to these results by the end of this year, but for sure we will continue by the next year to work in this direction. So this would be the infrastructure, the main infrastructure for all this kind of interaction among humans from one side and the robots on the other side. So,
yeah, no, because there is a startup in Berkeley by Peter Abiel who does exactly that. It's called Covariant.
Okay, we will check it.
And
okay.
Then there is the work of Anka Dragan on learning, on making robots not, collide with humans while performing collaborative work.
Very good, very good. We will check this for sure.
Right, and also, in general, this is a realm of roboticists, right? So not of an expert. So okay. You may want to look at that kind of work being done, but again, Peter Abiel and Anka Dragan reference on their papers, you can easily go to the important paper in this domain.
Thank you, Alberto. Thanks. We will take this as reference. Okay, so let me go on the different technologies and researches that we implemented. So for the first group, I give the presentation to Tiziano and then Paolo. Tiziano.
Yes, actually, partially addressing the concern of Alberto, my colleague Paolo soon.
That concludes the majority of today's.
Sorry?
No problem, go on, sorry.
We'll discuss, for instance, how robots may learn from surgeons, the different steps of a surgery operation. So this part is about building recipes and using formalism for building the model of a process of production. The first part is about research by the group of Franco, in which the cyber-physical production system is modeled using SysML, which is an offshoot of UML. And the main, let's say, mathematical tool to achieve capability of verifying, but what is being defined is what we want, is the assume guarantee algebra of contracts, meaning that different components, of course, we have to describe component-wise a complex system, the different workstations, etc. It comes with its own assumptions on the environments, guarantees on what it can be achieved by this specific machine, for instance, and the fact that all of these descriptions make sense, are, let's say, well described, is achieved through the assume guarantee algebra, and of course Alberto is one of the founders of this idea. So in this part, basically there's a formalization with SysML, and also different formalisms are used for reusing existing, let's say, descriptions like automation ML and ISA 95 descriptions. Then with algebra contracts, we verify that what is being described makes sense, and the algebra can be vertical and horizontal. And basically, we can also support design exploration and do some optimization by choosing in the design space a solution which is better for a given goal. You see some of the research outcomes, and especially the first one is a sort of the most important. It went into industrial informatics, transactions with industrial informatics, in which the full, let's say, philosophy of the approach is presented. Can you go next? In the second part, which is more technological, if you want, the idea is to map at different levels of abstraction in a hierarchical fashion, the models that describe the steps to produce a product. So we are in the realm of recipe production, so producing the different, let's say, plans for assembling an object, and these different plans are somehow sectioned vertically and horizontally according to the level of detail that we want to achieve, and according to the assignments of tasks to machines that we can achieve given the request of the let's say production line, given the raw materials that are available, etc. So this can be seen as a platform-based design application. This instead contribution is about using different formulas for planning, scheduling, and modeling at different levels the laboratory. I will only dwell on one of them, which is the formalism of temporal networks, because maybe less known to people outside of this research area. Temporal networks basically allow to specify, validate, and execute workflow and business processes. They have been used, for instance, in production planning for car assembly. They have been used to validate recipes, meaning protocols in a hospital environment. They are used in aerospace, like to put together different plans for autonomous vehicles on planets outside maybe the Earth, in which the vehicles must be able to decide what is the next plan, which is the most urgent in order to achieve a goal. For instance, they need to get some rocks for analysis, but before they may need to get more energy because their energy is being depleted. And so this requires a way of formalizing the plan and to decide the schedule in order to make sure that within certain constraints, the goals are achieved. And just to give a very, very short historical background, they were started by Ford and Fulkerson in the 60s, just as linear differences constraints. And they have been enriched in the 90s and in this century by adding constraints on, let's say, undefined and let's say on a limited information on controllability. I think that now I'm leaving the floor to Paolo.
Perfect.
Thank you, Graziano. I just want to pick up Alberto's question about the learning from human experience and human activity, and to extend it and to the two type of knowledge that I call top-down knowledge and bottom-up knowledge. So, Franco, if you can switch the slide, please. I think you missed one.
This was the first one? Okay.
So this is, we call it top-down knowledge representation. So how do we make these recipes? In this specific case, we are concerned about the procedure to carry out autonomous surgical intervention. These procedures are codified almost in algorithmic form in surgical textbooks, but they're not really easy to read. And so we are working on all these steps to extract from the text the actual surgical procedure, the actual action and steps that have to be executed by the robot. And here there are a number of sub-difficulty or sub-goals. So first of all, you see here, identify what are the procedural knowledge, what are the declarative knowledge that define the structure of the environment. But then there are other 2 points that are very difficult, actually 3 points that are very difficult. One is that, of course, these procedures assume a number of background knowledge, and we need to link these procedures to ontologies that somehow give the background of the description of the instrument, description of procedures, and so forth. Then there is the other point, which is let's call it common sense reasoning. So there are a number of information that are not available, not written anywhere, and surgeons learn in a very long training period. And so now we are trying to address how we can develop common sense information representation for these procedures, for robotic procedures. How do we give this information to the robots? So these are the things that we are working on. And this slide instead represents what Alberto was mentioning. So how can we learn from manual execution? I'm very concerned not only for this specific case, which is related to robotic surgery, but also to the preservation of artisan works, manual labor, other things that are fast disappearing in Italy because artisans are getting older and there are no replacement for them. And so one thing is to be able to learn to get a system to acquire the the steps of the sequence of action that they are doing. And we are using this hybrid approach, hybrid automaton or finite state machine, depending how you call them, where we first identify the different phases, and then within each phase, we are identifying the motions on which the robot has to execute the task. The second part, the continuous component, is well developed. All this, of course, is the work of my PhD students that are completing their PhD. And the continuous part is characterized by something we call the dynamic motion primitive, and so the motions can be represented by differential equations that have a forcing term that allows the robot to something like a potential field approach, and allows the robot to follow a given trajectory. The interesting part of this approach is that is scalable, is defined in a affine space, so it can be translated, rotated, zoomed in, zoomed out, and so it's very, very easy, adaptable to different situations. The identification instead of the, go back again, Franco. The identification.
The proposal to try to short a bit.
Yeah, but give me a couple of seconds more. The identification of discrete components instead is very tricky because it's we use a hidden Markov model approach, and so it's like a decoding, but the data are very tricky, and so. But I think we are reaching a very interesting result soon. And of course, we don't have the capability of getting a spin-off company with this thing. So if Alberto has any suggestion to how to find money to fund this initiative, they're very welcome. Another thing that is we're working on is identifying the causal relationship between different phases, different data in a plant. And this is the thesis of Giovanni Menegrosso, and we are trying to apply this to the ICE laboratory, but in the ICE laboratory, all the data are discrete data, and instead here we are using continuous data, so we are trying to figure out how to apply them to this situation. And then finally, and now you can switch, is the addition of sensor to instruments. In the case of surgery is very critical because surgical instruments are not instrumented, and so we are trying to develop small sensor or inserting sensors into 3D printing devices that can also be used in industrial application, and allows us to collect the data that will help to identify better the phases of a task. For instance, all the segmentation that I mentioned earlier are only based on kinematics data. Being able to use also force data and torque data will allow us to have a larger space and be able to do a more precise specification. So this is sort of the future of this research, and we'll apply it very soon, hopefully, to the ICE laboratory. And now Franco has disappeared, so all this rush, and where is Franco?
So I think Graziano is the host now. So Graziano, you have to put up the slides.
Yes.
But I don't have the slide because Franco has the word set. Maybe I can try to download from the.
Hey, Franco is back.
So, sorry, I've had a problem. Okay, sorry.
No, I'm done, Franco, so you can switch to the next speaker.
Perfect. By the way, to the committee, if you have questions, I don't know if you prefer to do them during the presentation or if you like to maintain them to the end, as you like, okay? We try to maintain the fixed schedule that we have, but in any case, you can stop as you like. So the next group of slides is related to 3D printing. Andrea, okay.
Yes, I think it's not a group, but just one slide, maybe.
Yep.
Okay. I will describe some work that we have made related to computational design. In computer graphics, people is working to create methods for easily and quickly design shapes and objects that can be printed, not only, but can be also 3D printed, as we can do in the ICE lab. And on this topic, Filippo Fani, that is the PhD student working on this, has developed a new method for creating object with decoration over them. We can apply different kind of decoration in a regular or non-regular pattern, as it can be seen in the picture and on the left. The method is based on sampling points regularly or not regularly on the manifold, and placing decorative elements that then are deformed, simulating, even if not in a purely physical way, deformation that simulates, for example, the deformation that we can have in real world sculpture made of clay, for example. We succeeded in imitating sculptures that are actually made by our artists on clay. And we also developed a pipeline, that is the one on the figure on top right, that allow us to scan with a 3D scanner the shape of a real object, and then design a decoration made of this decorative element over the geometry of the object, then decompose this shell of decoration in an optimal way to be printed with a 3D printer, and then to attach the decoration over the object. And we have demonstrated this with the Ice Lab printer. And this work has been published on ICM Transactional Graphics and will be presented at SIGGRAPH 2022. Philippe is also working on another side project that is related to something that we wanted initially to demonstrate in the Ice Lab, that is legalization, the idea of decomposing an object we can scan still as well with a scanner in the lab. We can decompose it in bricks, like Lego bricks, and we can then assembly, putting together the bricks. And the problem here is to try good heuristics to decompose objects in a collection of bricks that can be actually be built together. And also we have developed a method to decompose the object in a combination of standard bricks and custom bricks that are adapted to the border of the object, that can be printed with a 3D printer, resulting in an approximation, a better approximation of the object. And we are currently working on it. However, preliminary results on this work have been already published in a Eurographics Italian chapter conference.
Very good, Andrea. So this part was still related to transforming specification into the correct recipe and program the entire the entire production line. All software is working on top of the computing architecture. Graziano described the results on this.
Okay, thanks, Franco. The starting point here is the fact that the design verification of robotic software is a very complex activity, which involves a lot of analysis of many functional and also non-functional requirements. And for addressing all of these requirements, the software for robotic application is often executed on a hierarchical heterogeneous computing architecture, where the different software components are mapped from the edge to the cloud. And to solve this problem, in the ICE laboratory, we developed a 3 layers based methodology. At the very first layer, on the top, all the software tasks are executed inside some robotic operating system nodes. Everything is simulated, and this is done to achieve a first result from the point of view of the functional verification of the whole system. When you are happy with this first layer, you can go down to the second layer, where there is a first mapping of the different tasks on the computation unit. Here, the computation units are the real one, but the dynamics of the robots and the rest of the robots is still simulated by using some 3D simulator. But you can start to verify also the non-functional aspect, like, for example, performances or timing or other issues related maybe to privacy, security, etc. And when you are happy also with this layer, you can deploy the actual software on the real system where all the simulated parts are removed and the software runs on the robots. To achieve this result, two main tools has been exploited that are the Docker system for the containerization of the different components to address the portability issues, and the Kubernetes for orchestrating the mapping between tasks and heterogeneous architectures. This part has been carried out mainly by the group in parallel heterogeneous computing architecture led by Nicola Bombieri. But this is the first part of the story. The second part, next slide, thanks, okay. The second part is the verification. The verification that needs to be performed to assure that at every layer of the design methodology, everything is going well. And here we start with a set of assertions. This can be manually written or also automatically generated. We developed, for example, an assertion miner that extracts the assertion in an automatic way. And then these assertions are synthesized into checkers or monitors that can run inside the architecture together with the software task. The problem at this point is to avoid that the verification tasks negatively affect the execution of the software task. For example, if we have some real-time tasks, it could be that the verification checkers steal some CPU time from the software task, and this can lead to a failure of some deadline. We want to avoid this, and so we define a dynamic orchestration mechanism that allows to run at runtime the checkers without impacting on the software tasks. This is done by balancing the CPU usage of the different nodes of the different computation unit with the latency of the answer related to the verification tasks. The goal of the dynamic orchestrator, which is based on a MILP, is to avoid the saturation of the CPUs with verification tasks to leave space for the software task, and concurrently to avoid a very high latency of the verification tasks. And this is done, let me say, by applying different level of accuracy according to the goal that we want to achieve. This is the part mainly carried out by my group on verification.
Very good, Graziano. So this part, data management, which is now in the previous part, are related to the software infrastructure, which is not directly a part of the demo, but which is fundamental for implementing the entire demonstrator. So Damiano now describe the data management.
Okay, thanks, Franco. As Franco said, actually the architecture, the data collection architecture is a key element that is an enabler for the different services offered in the lab. So here the problem is that we have the data produced by the sensors in the production line, and we have a lot of sensors, and we have to collect this data and for real-time analysis. So we have to monitor what is happening in real time, but also for non-real-time analysis of historical data. So for instance, if we have to perform some predictive maintenance, we need the data. So this complex environment requires a set of complex solutions, both from the protocol point of view. So we have different ways of collecting the data asynchronously or by pushing or pulling from the sensors. We have different type of systems. So we have a distributed architecture and a distributed storage. and also different ways of querying the data and analyzing the data. So this needs different algorithms and indexing for doing so. Another aspect of collecting the data is also the network that is used to collect this data. So we have a large amount of data, so we have also to design a network that is able to collect this data without saturating the network capacity. So here there are different people contributing to these aspects, myself and then Elisa Quintarelli and Davide Quaglia for the networking part. Next slide. The other, one of the systems employed by the data collection architecture is a pub-sub system where the data are produced by a data producer and then they are consumed by the different applications. And since we have a lot of sensors, then we have to be sure that the data, the sensor that communicate the data is authorized to do so. And so we have authentication and also authorization. That means that the data, the different sensors can communicate only some specific types of data. So since these systems has not been designed with scalability in mind, then we have to add, in particular the group directed by Federica Paci has to add this authentication and authorization to one of the most used system, that is RabbitMQ.
Okay, good. Thanks, Damiano. So let me now move to something which can be seen during the demo itself, that is mixed reality. Andrea, you can go on restarting after your first presentation.
Okay. Next slide. Okay, in the demo, in fact, we will demonstrate the use of mixed reality technology, namely of the use of HoloLens head-mounted displays to see the actual state of the machines with the overlaid information over the real world scene. And in general, we are doing several research works on mixed reality and virtual reality topics. First, we are working on interaction, because in virtual and also in mixed reality, there is the problem to interact with interface elements that are floating in the space, and also with the virtual objects that we can insert in the scenes. And we try to develop a natural interface, in the sense that the reuse motor program that we are used to apply in the everyday interaction with the objects around us. For this reason, we are working on gestural interfaces that can be extremely useful in this kind, both to interact with the element of interface, but also with the virtual object, for example, to grab, scale, rotate objects in the 3D space. And we are developing a recognizer of gestures that exploits the tracking of fingers that is provided by many head-mounted displays of the last generation, like the HoloLens 2 or the Oculus Quest headsets. In particular, we are trying to developing methods to recognize gestures of different kinds of line. And as this kind of recognition requires machine learning, the first activity to do on this is to create data sets of gestures, of sequences of tracked fingers, and use these data sets to train recognizers. And in the last year, we created novel benchmark for heterogeneous gesture recognition, online gesture recognition, that was used to organize also a contest on which 5 different groups submitted their methods to online recognize the gestures of the dictionary that is represented in the picture in the slide. And the outcomes of this contest were published in a journal publication on Computer Graphics Journal. In the meanwhile, we also worked to develop a demo of online recognizer attached to the HoloLens. And the outcome of this research and implementation is the other paper cited here that demonstrates an online recognizers working on recognizing several kinds of gestures using in a HoloLens 2 application. Next slide. Okay, another research topics we are on which we are working related to virtual reality. In this case, that can be also demonstrated, for example, in simulation of the ice lab that we have already set up, is related to simulator sickness, because when we are immersed in a virtual environment, there may be some problems related to the so-called simulator sickness or virtual reality sickness. That is typically depending on the fact that we have to navigate in virtual space standing still. So there is a problem of mismatch between different sensing systems. The most recent research that we have done in this is related to the testing the effects of different rendering methods of virtual content that can reduce the sickness perceived by the users in a virtual environment. Namely, we implemented methods for foveated rendering and simulated foveated rendering. That means that we smooth the details of the images far from the location where the user actually is looking, because this may reduce the perception of motion that is felt when we move in the virtual environment. We performed a user test demonstrating that there is actually an effect of reduction of the simulator sickness, but even if only for the person that are much more sensitive to this sense of sickness. Finally, next slide, another very important topic related to virtual world creation and mixed reality simulations is related to the simulation of the human body. Here we have a very a lot. There is Umberto Castellani with his group that is working on development of virtual human models that can be derived by real captures of humans from reality, from different kind of 3D scanning, and automatically are transformed in posable models that have associated rig and skinning method that can be used to pose the models in the way we want, and to animate these, for example, following the motion of a tracked skeleton, or following the path of a planet in some way by a simulator. And this is very important, not only because we may use human models in a simulation or of activities on the lab, like the ice lab, but also, for example, because in working on a lab simulation, on a production plant simulation, ergonomics aspects are very important, and human body modeling is extremely important also for analysis of ergonomic analysis and also analysis of risks and so on.
Okay. Thank you very much, Andrea. So we finished this part. Now some other information about the technologies that we implemented in ICE for image analysis. Francesco?
Yes, thank you, Franco. So in these two slides, I will present a little bit about the image analysis work we did in the project. Actually, other parts will be presented by Davide Quaglia in the Opera because are strongly related to the Opera 4.0 project. But the general idea here in these two slides is that image analysis can be roughly divided in two different levels of abstraction. So this is the first level of abstraction where we are at a lower level, where we have to acquire and pre-process the data to generate a set of features that then can be analyzed at a higher level of abstraction. And in this case, we the main part is that the ICE lab is a very complex environment with lots of occlusions, a lot of objects and people inside. So when we want to analyze people in the environment, we need a distributed system. So one camera or two cameras is not enough. We need a lot of cameras. We actually have a set of 10 cameras right now installed in the lab. And there is this B-Fine system. This is the main work of Nicola Bombieri and his group. And this is a embedded system. So it's a set of 3D cameras that can that are temporally and spatially synchronized, and they acquire data from people in the environment, and they can directly reconstruct the skeleton on the embedded device. So with Jetson, basically it's NVIDIA Jetson boards, and then they pass through the network only the data, so the skeleton data, the key points. And on top of this, we can plug also other applications like the detection of falling people, or for collaboration with human-robot collaboration. We can plug a lot of different applications on top of this system. And if you can go to the next slide. Yes, this is a higher level of abstraction. So once we have the data acquired and pre-processed to extract some features, we can do a lot of different applications like people re-identification. In this case, instead of tracking people, we also have some more basic applications like tracking and this kind of stuff. But in the case a person exits from the environment and then comes back again, we don't need to do association. Again, we can use re-identification algorithms to basically assign the same ID to the person, even if we lose it from a few frames or even minutes. And then we have other kinds of applications where we want to understand the behavior of people. So this is particularly important for security or for safety reasons. So if people is going to do some having some dangerous behavior, maybe not being very careful in approaching some machines, or also if we want to analyze the different roles we have into the environment. So maybe there is a user which is more trained and is trying to speak with or teach to untrained user in the environment. We can have this kind of reasoning also for alerting some other systems to react on that. These are a few works. And just one more thing I want to say is that all these parts are based, you can see images that are not related to the ICE lab, but all these things are actually going to be embedded in the ICE lab through the Opera 4.0 and other related projects. Yeah.
Very good. Thank you very much, Francesco. So we just arrived more or less, okay, we passed the 1/2 of the presentation. We are perfectly on time. So now let me go to a very large and important part of the researches that we made. That is Riccardo, go on about advanced robots management.
Okay. Now please stay on the previous slide, Franco. Just to give some context. So this block of slide refer to the control of 2 mobile robots. So we have 2 Kairos by Robotnik in our lab with each of them has an UR5 manipulator on top. And we have 2 robotic manipulator, 2 cooperative robots. So the KUKA lightweight robot and the dual arm Yumi robot in the assembly cell. So in the last 2 years, actually, we are working mainly on 2 tasks. So the pick and place, so just to collect the single part that will make our gadget, and on the assembly of the gadget. So I will go quickly. I will quickly recall the different technology that we developed in these 2 years. And as you can see, for the same problem, there are actually more than one solution. And this is partially due to the fact that there are different groups that approach the same problem in different way in our department. So, okay, let's start with the mobile robot. So, to plan the trajectory for the mobile robot, we rely on the POMDP technique. So this means it is the acronym of partially observed Markov decision process, and this allows us to take into account the uncertainty about both the robot sensing systems, so actually the measurement noise, biases, and so on, and the environment itself. And then we can synthesize optimal policies according to specific reward function. As you know, the method is based on the theory of probability, and the key concept is the notion of belief. Unfortunately, POMDP has a scalability problem. So to overcome such an issue, the partially observed Monte Carlo plumbing, so POMCP, has been implemented to have a powerful approximate algorithm. So on top of the planning algorithm, actually we need to implement a mechanism to avoid undesired actions. So next, please. Okay, so the first approach is rule-based. So it prevents by design the possibility to select a dangerous action. And as you can imagine, it is mandatory in this case to properly model the sources of uncertainty in order to have such a structured approach to be effective. The second approach, please, next slide, Franco. The second approach is complementary and consists of developing tools that are able to explain why the AI-based algorithm actually make their decision. So here, of course, it is a very big and hot topic nowadays of explainable AI, trustworthy AI, and so on. I would like only to mention that recently the EU published a proposal to regulate systems embedding AI algorithm that is called AI Act. And I think that this will play a role also in the industrial scenario anytime this kind of algorithms are embedded in the control architecture. So next. So the next one is about how to formally prove guarantees, and in this case for deep reinforcement learning solution. So a group in our department worked on this topic, And the focus again here is to avoid dangerous and potentially harmful action in a safety critical scenario as our lab, so in our human robot scenario, collaboration scenario. So next, Franco. So and then we move back on another. The planning problem. So we have more than one robot. So actually, in our case, we have two mobile robots. So the approach that we are developing, is overkilling in our scenario. But of course, we want to generalize. So the idea here is to develop the centralized algorithm. So in order to allow the multiple robots to reach a common goal or common goals by properly sharing subtasks. So in this case, it is mandatory to be robust against unexpected events, such as a human walking in front of a robot, unexpected obstacle, fault, and etc. So this means that each agent must be independent of the others and be able to sense the environment, understand what's going on, make a decision, and then finally move in a, of course, a collision-free path. So this is what concerns the mobile robot. Then the second part is the assembly cell, where, as I said, we have two cooperative robots, a KUKA lightweight robot that is holding the screwdriver, and the dual arm Yumi robot by ABB. So the goal here is to assemble the different parts. So we actually have a top and a bottom cover and the electronic board. So what we need here is to recognize these pieces, then to plan the assembly activity, to assign different tasks to different robots in a dynamic way. So we don't want to hard-coded RC, but we want to be flexible. And then to plan the motion of the manipulator arms in a robot-to-robot collaboration scenario. So to do that, we actually have to integrate several vision-based algorithms and other AI-based algorithms. And we integrate this algorithm with a standard supervisory controller. So you'll see later that actually we developed more than one supervisory controller. And another thing is that since we have to move the robot when they don't interact with the environment, but they also have to interact with the object and between them, then we have also to implement force control algorithm to make the interaction safe and, of course, reliable. So, next, please. So here is now we are at the problem of how to manage the task planning. So how to assign tasks to more than one robot to cooperate in order to assemble the gadget. So we try, as I said, different solutions according to the different, to the previous experience of the different groups. Here, we have the solution using answer and set programming. ASP is actually a popular tool for addressing task planning. And this solution actually goes in the direction of the explainable AI, because the formalism is, of course, easy to understand by a machine, but also to humans. And I think that this will be a key point in our architecture if we want to be, easy to understand to the operator. Okay, next one. Okay, the other another important task is simulation. So we are we are dealing in the ICE lab with very complex tasks and with expensive devices. So often it is actually better to try algorithm, so motion control algorithm, force control algorithm in a simulation to avoid damages to the robot and actually the equipment. So even if in the ICE scenario, we consider only a rigid body, rigid object, so actually we have two covers and the electronic board. However, it is well possible to that in the future, the robot may interact with the deformable object. So how to handle the deformable object is actually a very challenging problem in robotics, and the simulation is an important tool to understand how to design the algorithm to handle this kind of object. And also here we leverage on the experience we gained working in the surgical robotics, so in the surgical scenarios. So in this case, we were able to integrate finite element method with a neural network and other solution to have not only a very accurate modeling of the physics, but also a very fast and a very fast simulations. So next one, please. Okay, so the list of paper in this slide actually cover another solution on how to model the knowledge about the task that we have to execute during the assembly. So here we use actually state chart. So actually hybrid, hierarchical finite state machines that works actually in parallel. And so this is another solution with respect to ASP and the other approach that I showed you before. And this is my last slide, but there is another key point that I would like to highlight. So computer vision is a mandatory techniques in order to get and improve at runtime the 3D model of our environment. So while we assemble the different pieces, the environment changes. So we need to update at runtime the model in order to always design a collision-free trajectory for the robot or interact with the gadget when we need and where we need. And this is the first point. The second one is about the registration. So in the assembly cell, there are several robots, several cameras, and of course the different components that will make our gadget. So we must be sure that all the reference frame are aligned in order to, of course, assembling them in the proper way and then deliver the final object on human or in the pallet for further test. I think that's all for this part. I went very quickly, so because there are actually very complex techniques. If you have any question, please feel free, and I will try to reply, or I will involve some colleagues. Thank you.
Very good, Riccardo. So
I was curious about the explainable AI story. Yeah. I mean, this is you say that something could be understood by humans. In what sense?
Okay.
Because that is not in general the notion of explainable AI. So I want to understand, what do you mean by that?
Okay, so if you have if you have a deep learning algorithm, then it is very difficult to understand what is going inside.
Yeah, of course,
yes. A huge black box with millions of parameters. Then
exactly, right.
So actually, this is of course my feeling. Probably people working on deep learning will give you a different answer. So, to me, the solution is to use the output of this algorithm not to take a decision, but to trigger event in a more structured formalism, like a state chart or ASP. So using deep learning algorithm as a soft sensors and explain the knowledge that is needed to execute a task using different techniques, more standard, I will say so, coming from the supervisory control, will make the overall description of the control architecture easier to be interpreted by the operator. So we use, for example, state chart in the surgical environment to model a surgical intervention. And even if we use also deep learning technique to trigger the event, then how the system should model the procedure is easy to understand from machine and also from the operators. Maybe, Francesco, if you want to say something more about the explainable part as a computer scientist, maybe it is Francesco?
Because what you are saying, describing to me is a mixed control architecture in which the neural network takes some kind of input from the sensory world, and then it translates into an action that takes place in a standard control.
I'm a control engineer, so I'm a little bit
I
biased.
understand. Yes.
So I would prefer to use machine learning, deep learning in such a way.
No, I agree, but that doesn't mean that it's explainable, because even the input that it gives to the standard control has to be explained, and so that is not clear how it comes. I mean, so it's an input that comes from the sky, right? So that's all.
Yeah, of course, but if you use this input to trigger events, then you can rely on past state or to use some statistical approach to weight actually the input that are coming from the neural network and whatever, to see if the results are totally crazy or make sense. And then you can use them only when we are enough sure that they are reliable.
Yeah, okay, we take it offline.
Okay, perfect, thank you. So let's move now with Davide to the part related to safety in a production environment, which is the joint part with the other project that we already mentioned, and that is Opera 4.0. So Davide.
Yes, thank you, Franco. Yes, the next slides will address the topic of safety of the production environment. Of course, the demonstration scenario is a production environment in which there are humans and machines, for example, robots. And one important aspect of manufacturing is safety. Even if this is not a functional requirement, is something extra functional, but clearly very, very, very important. And we tried to address the safety aspect in a industry 4.0 perspective. And so with a lot of artificial intelligence, connectivity, and so on. The first aspect we addressed was automatic safety monitoring. In particular, in a production environment, people need to wear personal protective equipment, for example, helmets, gloves, glasses, mask, as in the current period. And we developed a automatic monitoring system based on visual inference and based on a distributed system of cameras connected with a network, which provide the detection, the real-time detection of mask related to different workers inside the environment. Next slide, please.
Sorry. Okay.
The next topic was related to the automatic recognition of human presence and related events, for example, false, and the identification of pair of humans in the production environment. And this is a very important aspect, again, for safety, but cameras may have privacy and coverage issues, and artificial intelligence, so visual inference, can be error prone and time consuming due to non-automatic annotation, data annotation. So the solution provided by our colleagues was the exploitation of Bluetooth device and Wi-Fi channel information to estimate the occupancy of the environment and the identity of people. And furthermore, by using wearables, it was possible to perform automatic data labeling and, again, person identification. Next slide, please. Another problem is the interaction between humans and robots, which is an important aspect, not only in collaborative robotics, but also in a traditional approach. So robots may collide with humans, of course, and currently, to avoid the damage of collision, robots are programmed to stop in case of collision. So the problem is not damage, the problem is the lack of production efficiency in case of collision. We address in this case we addressed the problem of the estimation of the time before a collision in a mixed human-robot environment. So how in advance, how long in advance it's possible to estimate when a collision will happen. And this aspect, this time is important to address collision in a proper way. So, for example, by reprogramming the trajectory of the robot, by providing an alert for the human, and so on. So it's important to understand the time margin before a collision. Next slide, please. Okay, and another aspect, this is quite a new aspect, is an ongoing part of the research related to brain-computer interfaces. So again, for safety, we addressed the problem of risky situation due to the psychophysical state of the worker, for example, in case of lack of attention, mental load, stress, and we are working to develop a wearable passive brain-computer interface to monitor in a non-invasive way the condition of the worker, again, to provide in advance some alerts to avoid risky situations. And this is the particular research problem here is to embed all we need in a personal protective equipment inside a helmet, and to provide a robust artificial intelligence framework to detect the psychophysical state of the worker, starting from brain signals. Next slide, please. Okay, this is the last, but probably the most important aspect at the end of everything. So you can imagine that up to now I described a lot of sensing approaches, neural signals, pose estimation by using cameras, person identification by using Bluetooth, again, mask identification by using neural networks. We can see that everything, they are a lot of smart sensors to collect data from the production environment. But at the end, the point is how to merge all this information, again, to prevent risky situation. So the idea is that the problem is that the interaction between humans and machines may deviate from the nominal behavior, the expected behavior, and frequently when there is a deviation, then there is a risky situation. And so in this slide, we show that the solution is the analysis of execution traces from all of these smart sensors to detect deviations from the nominal behavior and to track such deviation and to understand the causes of future risky situations. Of course, yes, just last word, of course, which is an introduction to the next slide. So safety is very important, and we try to analyze safety in a 4.0 manner. So by using a lot of data, a lot of data transfer, a lot of information. Of course, this raises another big problem, another big concern, which is privacy. And this is the topic of the next part of the presentation. Thank you.
Okay, thank you very much, Davide. So now we arrive to the last two parts of our today presentation. This one is related to security and privacy. And Federica, okay,
yes,
describe all.
Yes, thank you, Franco. So if you can stay a minute on this slide.
Yeah. Okay.
So I can give you a bit of context. Yeah, I will tell you next. So in the production line that we have created in our lab, we have several opportunity or attack points for security and privacy attacks. For example, the attackers may take advantage of vulnerability that are present in the devices, or they can take advantage of vulnerability present in poorly coded application, or they can even exploit vulnerability that are present in the users, like the workers or the operators that work in the factory. And in the project, we have focused our analysis on vulnerabilities and attack techniques that affect the device level and the application level. Next. So at device level, first line of work has focused on the definition of novel approaches to attack PLCs in an automatic fashion, in a fully automatic way. And this has been achieved by first automatically detecting which are the vulnerabilities that are present in the PLCs, and then exploiting this vulnerability to assemble an attack. Next. Another stream of work related to the device level is about the realization instead of an honeypot for PLCs. This honeypot is able to simulate the behavior of different PLCs so from different vendors, so that an attacker is tricked into believing and thinking that is actually interacting with the PLC. So the honeypot allows to collect data on real-life attacks that can then be used to create a formal model of these attacks, and also to develop new runtime detection techniques for these attacks, and also identify possible mitigation strategies to prevent these attacks. Next. At application level, instead, a first line of work is focused on verifying that the code of the application is robust against security attacks. So the work of the group by Mastroeni and Michele Pasqua has developed static analysis techniques to check that the code satisfies the specific property related to the flow of the data. So, for example, that the code does not disclose data that was not supposed to be disclosed. Instead, next, sorry. We also focused on the analysis instead of one of the key components of the attacks in general to cyber physical system, and also to the production line, that is represented by malware, by malicious software. So this work addressed the problem that malware using this kind of attacks use evasion technique like code obfuscation or self-modifying code to evade the detection from antivirus software or anti-malware software. So this work has developed a new analysis technique that can be applied even when malware use these evasion techniques, and on developing a formal framework for measuring how imprecise the static analysis of malware code is when this technique has been used. Next. The last contribution doesn't focus on the detection of privacy violation in the level of application code. So, for example, when the code in an application share personal information like the geolocation of a worker to an unauthorized audience, or make even them public. So, for this kind of to detect this kind of violation, there have been applied static analysis techniques that check in the code for situation where a source of private data, like the geolocation data, is propagated to what is called a data sink, where this information is disclosed outside of the T system. So, for example, is made public.
Okay, very good. Thank you very much, Federica.
If you have any question, I'm happy to answer them.
And we are arriving to the last part related to validation, verification, and testing. Mariano?
Thank you, Franco. So this part is, let's say, quite cross-cutting because it's related to validation. And many of the techniques apply to most of the steps because the quality of the product can be checked at several stages. For this reason, the first part no, just keep the previous one. As you can see, the first point applies to specific phases because the specific properties are checked. Why for the other two, we proposed that we basically conceived a dashboard that can be used to visualize quality aspects or let's say anomalies that occur in the process in a broader sense throughout all the production steps. Next slide, please. So let's start from the check that we perform on specific phases. These are on phases 4 and phases 6. And basically, they are meant to inspect the final product that, let's say, is produced. The idea is not to apply just to the demonstrator, but also to a more broad sense. For example, to check and verify biological materials, which is much more complex. This first line of research applied advanced optical coherence tomography for performing this check and also electronic impedance scanning. They are advanced techniques that can be used to check the quality of the production, not just at the end, but also during the production. Next slide, please. This line of work instead was devoted to check, to perform material characterization and identify materials and their properties of materials that are used during the production. And the approach was to use advanced transformation imaging, such as fluorescence reflectance. Next slide, please. Now we move to a more broad and cross-cutting verification that we apply to the production of the piece. In particular, here we do anomaly detection. They are multimodal anomaly detection, and they are helpful to identify anomaly in the sense that for coming collisions, to detect collisions before they happen, or to forecast failures before they happen. The idea, the final objective is to reduce human intervention. And the problem is that to achieve this objective, we have to deal with a numerous sensor and a quite different source of data that are typically noisy and that they should be handled in real time. The solution was to apply neural network, in particular exploiting results from stochastic mean field games, and consider their extension to large groups of interacting robots. The solutions that have been developed in this line of research are also, let's say, applied by our academic spin-off, which is HPA, in optimization of industrial process, logistics, manufacturing, and so on. Next slide, please. This other line of research also apply anomaly detection, in particular on two mobile robots that are available in the lab. And the approach here was to apply time series to data that are coming from sensors by scanning the log files available in the mobile robots. The idea is to use this data to learn a model of the nominal expected behavior using hidden Markov models, and to measure the current status, the current data that are available in real time in the robots, and identify whenever the data available from the robot in real time are distant from the nominal behavior. And here we use the notion of Hellinger distance to check whether there is any deviation from the nominal model. And these results prove to be more efficient and more, let's say, performing better than state of the art. Next, yes, thanks. Here, this is the last slide, and basically, to explain this slide, I have to recall the very first slides where a model-driven approach was proposed to create a modeling of the piece to be produced using SysML, for example. Using the same modeling, in our approach, we automatically generate a smart contract to be run in a blockchain that basically is meant to publish, record, and certify data that are collected during the production. The idea is that any end user or customer can use this smart contract to check the quality of the final product. The quality in terms of the process followed to produce the part, produce the piece, and also all the operational parameters that have been recorded while producing the particular piece. Because the operational parameters, for example, the rotation speed of the drill, might affect the final quality of the piece. The research in this line went on also by developing novel techniques to check the correctness of these smart contracts to avoid any mistakes or vulnerability in the smart contracts that might affect the availability and the validity of the final data. These techniques are based on the static analysis of the smart contract and also on the guidelines that should be followed while generating this contract. Moreover, in this line of research, we also develop a novel static analysis approach that has been integrated in the blockchain itself to turn static analysis and validation as a part of the consensus protocol of the blockchain itself. And this concluded the presentation. Thanks.
Very good. Thank you very much, Mariano. So that is, we just finished the presentation of all the research results. So the next slides are about exploitation and dissemination. If I like, we have time, I can briefly describe them, and then there is a lot of time for questions. Here you can see the number of companies that visited HICE in the period, and the amount of contracts, research contracts that we obtain. It's pretty interesting. And with respect to the idea of generating a demonstration labs like HICE it is, okay, we have been able to create spin-offs of this idea. So one related to the factory of the wine factory, okay, that is, it is a demonstration lab devoted to the production of wine, which is typical of Verona, and which is based exactly on many results, research and application results of HICE, for example, data collection architecture and all other stuff related to digital twin. We are currently implementing a similar demonstration lab on logistics, which is another important part of the economy of Verona, and there are some other ideas. With respect to dissemination activities, yes, there is a list of meetings and on operations and presentations that we made to companies and to group of users of the territory. Here there is the list of workshops that has been done during the last summer with respect to research results of the HICE lab. And finally, as you already know, we have a website, a YouTube channel that we frequently use for explaining our results and for performing dissemination. Okay, this is the last slide. So we are open to any questions that you can have about this presentation. I can eventually go back to here. That could be a source of ideas for your eventual question. In the case there are no questions, no problem. This was a
more than a question, is a comment, right? So the results that you presented are certainly impressive in all different aspects. Now, it's not so clear to me how the various parts that people presented are going to be put together in this demonstration. So I don't see the floor, the milestones that each of the subgroups have to deliver in order for the entire picture to come together. And also I saw in your slides that you had the plan to conclude this work in 1 year, so at the end of 2022. Now this is a lot of work to put together, because each of the components you can do, but putting it in a real flow like Industry 5.0, as you call it, is challenging. Also because I'm not convinced that the actual architecture is the right one, I may say. So the point is that instead of saying generically this is the factory of the future, I would say this is the manufacturing line for watches, just to make anything, right? Or to the manufacturing line for pasta packaging, right? So you have to go one level down. Otherwise, this one is just a collection of technologies that somehow are put together. But it doesn't give me the feeling that you really understand what it takes to do the entire step needed to come to a new conception of industrial control and the like. Okay, this is all.
Yeah, Alberto, thanks for the advice. By the way, I think that all the slides that we skipped during this presentation for lack of time, that is a slide from 11 to 31, are slide that describe the current level of the implementation of all the technologies with respect to the specific phase. So there is written exactly how we are with respect to phase 1, phase 2, phase 3, and so on, and what exactly we would like to do. We did not report the Gantt of all the activities, you are right. We have an internal set of milestones. And for example, let me go back with respect to this list. We arrived to perform the complete design of the pieces that we would like to assemble together. You have right, this is a general factory. We can say that we try to consider the production of smart objects, okay, with the idea that we have pieces of plastic or other material assembled together with an internal electronic stuff that gives the smartness to the object. Such objects can be also wearable, so we can say that our factory will produce wearable objects. Another idea, we use the term gadget because we didn't complete this agreement, but we had some discussion with the exhibition of Verona, which is just in front of the laboratory. And this exhibition asked us to be able to produce gadgets for people attending the different exhibitions with different shape with respect to the kind of exhibition. For example, Vin Italy, which is typical, could be the generation of a gadget with a bottle of wine or so on. So this is the mix of production that we would like to tackle. And we have already some implementations. That is, there is the implementation of the mess, which is completely reconfigurable. There is more or less the implementation of the mobile robots able to pick up pieces from the storage, vertical storage, not complete, but very close. We have the complete control of the mini pallet belt that distributes all the stuff through the different parts of the production line. We have the visual control, okay. The assembling part is more or less completed. The electronic configuration is is the last part because we are still waiting for the machinery that should arrive in a couple of months. All the tracking part that is able to recognize people, workers moving in the lab and making particular kind of movings is okay, has been implemented. The data collection architecture is implemented. So if you consider a percentage of this demo, I think that we are close to 80%, and our first version should be ready in 3 months. And so the final version should be ready by the end of the year. In any case, you are right. We did not report a specific Gantt with all the deadline. And this will be the first task that we will do in the next meeting of the project.
Now, another thing that is about the computing architecture of the ICE lab assets, right? So if indeed the kind of Industry 5.0 approach that you take, there are some monster computers like multi-core platform, 900 CPU cores and so on. Do we need that kind of power? No. So I assume that this computing architecture is actually serving a much bigger goal than just the Industry 5.0. Am I correct?
Yes, you are right. About the computing architecture, we try to identify the technology to move software, Docker software, from boards, from computers, edge computers, up to the HPC that we have. So perhaps you're right, it is too complex with respect to the standard software, but it has been used to check and to verify and to show that it is possible to move the same software from the robot, like it's going, directly, partially to the computer architecture without recompile it, without changing it, by preserving performances or by scaling performance. We are using computer architecture for the data collection, by making experimentation about scalability. So in the laboratory at the moment, there are no more than 30, 40 sensors. In the case there would be 100, 1000, what's happened. So we made some check about the scalability. But right, we are not using the complexity of the entire computing architecture that we have.
Yeah, well, I mean, if I had to present it myself, what you got is that I would use this as a demonstrator. That's fine. So you can put various technologies together, but I would also underline the importance of building long-lasting infrastructure, right? Yep. Because somehow, if the grant that you got, right, is just about, you know, this particular aspect, it will not be enough. I mean, I would like to see something that continues after the grant is over, right? That is left for the university to build upon. And so the fact that you have, you know, this infrastructure like the lab assets, right, it's a positive, but it should be made it clear that you're also building for the future.
Good point. Good point.
So if I may say something. So yeah, I think I had you know, quite similar thoughts to what Alberto just said. I think it is really impressive, given all the work that you have done, and under each of the headings that was presented, right? You know, security, privacy, or data management, or robotic manipulation. I think there are lots of results which is natural and desirable, and maybe not all of them can come together in a final demonstration, which is also very understandable. But I also felt that, if I may just maybe articulate it in a slightly different way, I felt that in the demonstration that you are doing, as you said just now, you are trying to manufacture smart objects. But what is still not clear to me is that how is it that those smart objects could not have been manufactured without you doing this project? So if this project wouldn't have been granted and none of this work would have been done, is it the case that that smart object would not have been manufactured? Or is it that you are manufacturing this smart object in a different way, in a better way? I think that issue should be communicated or articulated better, right? That prior to this project, this is a problem that could not be solved, or this is a problem that needed much more time to manufacture, or this is a product that needed much more cost. And our aim, among the many things that we can do, right? Of course, this has led to a lot of research that has applications in domains way beyond, you know, this industry 4.0, like, you know, robotic surgery and other things. But saying that, you know, of course, it led to all these results, but this is something that could not be done or could not be done well. And now all of these results we have developed, parts of it can come together to improve this. And maybe we still did not achieve this final goal, right? You know, Alberto talked about this moonshot when we had met. And, you know, maybe we still don't have the moonshot yet, but, you know, at least we are on a path towards that moonshot, or we have even completed 20% of that moonshot. I think that articulation would be very important and, you know, will be appreciated by, I think, anyone, all the stakeholders, the funding agency, the general population, and so on.
Thank you, Samarjit. Good point. I can answer in this way. Obviously, we can imagine to have any other production line able to produce this object, that is, because it is a gadget. So, and particularly if you consider a specific production line which has been designed to produce this specific one of the possible objects that we are producing, the efficiency of such a production line is much higher, for sure. Our starting idea is to allow the complete reconfiguration. So the problem should be that the user at the beginning of the production line should select among a different set of objects without saying exactly, I would like to obtain object number 1, number 2, number 3 among a list, but I would like to collect together some requirements among a set of requirements, and the production line is able to produce exactly the object mixing the requirements. This should be the first stuff that must be shown, which is very innovative. The second stuff is that, the second point is that the entire production line, with respect to the variety of different machineries, from the vertical storage to the mobile robots, to the camera, to the robots, and so on, are completely configured. And this is another point which is unusual. It is not very likely. And then we have an integration among, and this is the final task, which is more difficult, an integration among workers, okay, and robots. This part is a part which we will probably allow only to touch and to identify only one small task that could be done by a worker or not. And if the worker is doing, the robots do not doing, and vice versa, but nothing more. Okay, we will arrive up to there. And this should be the starting point for following and further evolutions in which the integration among humans and robots would be pushed on. And this is activities for next years or for next projects. But based on this infrastructure that must be no longer developed because it is an asset of the department and all the researchers could be put on top of it. I don't know if I answered. Okay.
Absolutely. Absolutely. But I think that certainly answers, what I tried to ask. But if I latch on to the reconfigurability part, right? So what you are saying is that, look, what we have to offer is a highly reconfigurable manufacturing system. So then you decide what is it that you want to manufacture, and we will be able to manufacture that, right? That flexibility is being offered. Of course, this is from a research standpoint, this is very, convincing. But I think it also raises the natural question, right? That, if you have this kind of a technology, where is it that this technology is useful? So let's say I want to manufacture a particular product, right? I am your customer. I'm the customer of your technology. So I want to manufacture a particular product. Will it make sense for me to take such a reconfigurable or such a flexible manufacturing system and use it? Will that be meaningful for me in terms of the cost that I will have to pay, in terms of the production efficiency, or will it be much better for me to just take a manufacturing system that just does my job? So I think those kinds of obvious questions probably should also be answered in motivating this, right? Is it really like just a huge, interesting scientific exercise, or does that, or what is the path forward, right? Can I take this highly flexible system and really, specialize it for particular domains, and will that then be cost effective? Because, my starting point is always the same. I think, answers to those questions were not there in the presentation. And given
it's a very good question. Let me try to answer in this way. If you consider all the companies that went to us to visit, usually they arrived and they started to say, oh, very complex, very impressive, okay. And let me focus on this specific technology that you implemented, because with respect to my factory, okay, I can extend my factory by implementing this part. So there are companies arriving to say, we would like to have a much more robotic operation, or some other that say, wow, the manufacturing execution system which is able to be reconfigured is very important. Some others say we need the data collection architecture. So we didn't find up to now one company which is interested to the entire flow. You are perfectly right. Perhaps we are some step further with respect to the actual production. But if we take slices of all this infrastructure, we have a lot of companies that continue to ask us to say, good, let me try to extend this and to put this in our environment, in our, so yes, you are right. Perhaps we are a bit in advance, but it is typical of the research to try to anticipate events.
No, absolutely. But and I think that's also perfectly valid. But I think then when you write your final report, or when you sort of conclude this exercise, I think then it would be a good idea, in my opinion, to look at it at least from this perspective, that look, our main goal was to come up with a completely flexible manufacturing, highly configurable manufacturing system to the extent that was not possible before the start of the project. And I think it is still worthwhile to give some thoughts as to who might potentially, it is true that, no one has come and asked for that entire technology, but who is it that could potentially come in the future, or what could we do to enable such a potential customer? But what has happened as a process of this, maybe a slightly theoretical goal, is that there were lots of individual point technologies that were developed, and those point technologies are useful in existing contexts, right? And given that you have had those interactions with real customers, maybe also make a compendium of that, right? Make a list of where each of these technologies could be useful. And that would also be a learning exercise. And, I think a very, very useful outcome from this project.
Okay. Good point. We will follow your advice. Very good. Other questions? By the way, you know that we are expecting that you fill in the report, okay? And we propose to you also deadline if possible, because this allows us to continue in the...
I think end of February is what you said, right?
Yeah, exactly. Obviously, in the case you have question of any kind, okay, send us emails and we will answer to your questions with emails and documentation.
Okay.
Yeah, thanks.
Franco, as for me, yeah, it is very nice to see that you have a more concrete demonstration scenario as a testbed for technology integration. I hope that it could be successful to show the concept of your reconfigurability as well as integration with human workers and robots in the system in the next year. It will be very impressive if the demonstration is successful, I think. One question I have is, I think you answered that my question in your comment, but then I think reconfigurability is important because, if we change the factory, the company is changing, the manufacturing company is changing model or product, then they have to reprogram many things, including robots, and it takes a long time. So actually, automation is a kind of important part of successfully demonstrating reconfigurability, because you need to have some automated way of restructuring software or reprogramming robots, whatever. But then this is a little bit challenging thing, because as you mentioned, how much you will automate till to the end of robot doing everything, or as you mentioned, then there must be some good the division of human workers and robots, so that there can be some parts that can be well automated, but then there can be some parts it's a little bit hard to automate unless you use very high sophisticated artificial intelligence technology. So that part was my question. So, but I think you are already aware of that thing. I noticed from your answer. So I think it could be done well. So I expect to see some good results in the coming year. Okay. That's my comment. Yeah.
Very good question. Let me say that I can give us a first answer, but then I leave the answers to all the colleagues. That is, we have a first solution, which is the basic solution, and which is the implementation that we are doing. And this solution rely on basic operations, which can be implemented by all the different actors of this complex architecture. So in the high-level model of this complex architecture, for example, we have some recipes which are divided in 3 levels. We have 3 levels and a hierarchy of operations, and all the logic infrastructure that we have is able to map a receipt among all these basic operations. But we have to know such basic operations. So the reconfigurations is a way to assemble in different orders all such basic operations. This is my first answer, and it is related to my part. But then there are some colleagues which are implementing most advanced techniques, like Paolo that described before, the way to extract behaviors from human movings or from textual data and so on. And this could be some more advanced results. I don't know, Paolo, if you would like to say some more about to answer. Microphone.
The microphone will
okay,
help.
Perfect.
Certainly, there are difficult problems. As far as the textual, the extraction from text, I think we can have an alternate way to define the recipes, and so this is a feasible approach, implementable. I don't say in a short time, within next year. In terms of learning from manual operation, that's a very much difficult problem, and I'm not sure how far we can go. But hopefully we should have reached developed a good algorithm to do this segmentation, and we are testing it on artificial data. I think we will know in next few weeks whether the algorithm is successful to do this real data segmentation, and then we can apply it to we have all the devices in the laboratory to do the acquisition of the data, tracking of fingers and the kinematic position and so forth. So the data can be extracted also from industrial assembly rather than clinical procedures. So we should be able to do also the segmentation, but we need to transfer it to that specific field. So it's work in progress, very interesting, very promising. On the top-down knowledge representation, we can somehow promise that we'll be able to demonstrate it. The other one will show what at what point we are.
How much did you make progress on digital twin?
Which progress we are doing? That is, we have
digital twin.
Yes, we have different activities on digital twin. One flow of activity is related to the automatic configuration or generation of a digital twin starting from a high-level model like SysML. It is a kind of synthesis. Then we have other activities that try to mix digital twins of different abstraction level in order to speed up the global simulation. And then we have also some other activities related to what is called digital shadow, that is a digital twin monitoring data, which does not evolve with the synthetic data, but with the actual data. And again, in this context, there is automatic configuration starting from high-level models. And finally, there is the use of digital twin for simulating attack to all the different devices to check the security of the entire system. And Paolo also has some activities that has been described among the use of digital twins for simulating tasks in advance and to learn to robots how to move. So it's a technology that we are using on a lot of different areas.
Okay, thank you. Yeah.
You're welcome. So if there is nothing more, I think that we have to thank you really again for your time. And we know that Alberto must go to the next board meeting. So
yes,
we can
8:30. So I still have time. That's okay.
You have time for a coffee.
Just for coffee. That's fantastic. Okay, thank you.
Okay, so we hope.
Yes, thank you.
We hope really that the next review meeting will be in presence here, so we can show you all the stuff and we can go together to have dinner. So thanks again.
Yes. Yes.
All right. Thank you. Thank you.
Bye bye. Have a nice day.
Ciao.
I just wanted to, Franco, I just wanted to say that, I mean, in conclusion, I just wanted to say that I really find, and I think all of us find the work that has been done to be truly impressive. And although there were all this feedback on, what is like the common thread and what is a common demonstrator, I think I really appreciated also this slide that is, on the screen now. And the way you managed to put all of this together, and the entire presentation, I think, also sort of conveyed a very coordinated effort. And this is not easy that, so many people come together in such a big project. I think it not only speaks very well of all the people who did it, but also of, your leadership to bring everyone together in a coordinated effort like this. So
thank you, Margit. You are always kind, but thanks to all the colleagues, otherwise we couldn't arrive to this result. Thanks again to all. Bye bye. See you.
Thank you. Thank you.
Bye.
Ciao.
Thank you.
Bye. Thank you.
Thank you. Bye.
Bye.